Hi. So we're starting today with section 15.2, which is line integral of a vector field. Okay. So we need to define what a vector field is, and we have to define what's a line integral vector field. Now let's just do a review from the previous chapter, from the previous section. If we have a curve C parameterized by r of t equal x of t I plus y of t j plus z of t k, we can write it as x of t, y of t, z of t, and this is my curve, let's say, and this is a smaller than t smaller than b. Then in this case we said the velocity vector is dr dt is the variation of position over time, which is x prime of t, y prime of t, z prime of t, which is tangent, as we said, to the direction of it's tangent to c in the direction of motion. This is from a to b. Okay, this is v of t, for example. This is v of thing here is v of t. This is r of t, and we said s of t is the length from a position. So if I have, again, same thing, this is my curve, this is my curve C, and let's take the length from the initial point till the point at time t, if this is r of t. And if I want to know the length here, this is a function, because when you vary t, the length will increase. So this is called arc length parameter. This is equal integral from a to t of absolute value of v of tau d tau, and this should not be very strange, because now I have ds dt is equal to, well, to absolute value of v of t. So this is as if saying delta s is approximately equal to speed. So length is equal to speed times time. So this is what this is saying. And then, well, the length, well, let's do a review. I don't need it today. For the length, is integral from a to is s of b. That is from the initial point till the last point, which integral from a to b of v of tau d tau. Okay. And then we defined, so given f continuous, the line integral continuous function, let's be precise, continuous function, we define the line integral of f over c, integral over c of f ds. So I'm integrating my function over the curve now, which is still a one-dimensional thing. And this is equal integral from a to b of f evaluated at my curve times ds, which is, now I need to put the Jacobian, which is v of t dt. And this is the line integral formula of a function. And we showed many things, but let me, if you want to see more details, go back and watch the other two videos, okay, of the previous two lecture. Now I will start with, so definition. So a vector field F in R3 is a map that assigns to each point xyz in some domain a vector f of xyz equal m xyz I plus n at xyz j plus p at xyz k, or simply m n p. Okay. So what is a vector field is? So I have, now I'm in R3. Okay, this is x, this is y, this is z. And let's say at each point, I have a vector. Okay. The map that assigns to each point a vector is called a vector field. This can be in 2 dimensions, by the way. It can be in any dimension. It can be in n dimension. But I mean, I will give the definition in R3, and you can generalize to smaller or larger interval. Now, what are m, n, and p? M, n, and p are the x, y, are the x coordinate of the vector. So if this is my vector, it has an x, it has a y, it has a z. So it's m and p here are functions. So if I want to call the domain D, are functions from D to R. They are functions. This is a value here. It's a value. It's a value. And the whole thing is a vector. We say that F, well, that the vector field F is continuous if and only if M is a definition and P are continuous functions. There are many examples of vector field, and maybe the easiest example are forces. Okay. So now, wherever you are, whatever position you are on Earth, you have a force, many forces that are applied to you. For example, there's a magnetic force of the Earth, there's the weight, there are. So this is, for example, these are examples of a vector field, correct? Let's say also it's a particle that is moving. Let's say I have a particle P that is moving from point A to point B. As it's moving, there is a force applied to it, for example, which is the weight, correct? At each point on this curve, I have a force. So this is a vector field. Do you agree? There is the electric field, for example, weight, force of forces, let's say. There's the electric field surrounded by a charge. Just to tell you that they don't have to have motion in this case. Let's say I have just a magnet here, point magnet. And now this magnet creates a vector field. Do you agree? Sorry, this is so whether there are points around it or not, but at each point in space, I have an electric field, which is inversely proportional to the distance. So if I want to be more precise, this vector should become smaller and smaller. This vector should become smaller and smaller, because as large the distance, the electric field is smaller. Okay. There's a magnetic field. Also for a magnet, like in this example. Well, mathematically, you know, another example is given a differentiable function. So sorry, for this example given by a charge, I have here an electron. Okay, so let's suppose it's an electron, and around it there is And for magnetic field, you can take the example of a magnet. Create a magnetic field. Now, given a differentiable function, f of x, y, z, this is a function now. Gradient f, which is the vector fx at x, y, z, fy at x, y, z, and f sub z at x, y, z, this is a vector field. And what does this vector field represent? Remember, this is a vector field that is orthogonal to the tangent plane. So this vector field represent, no, but not mathematically, this is geometrically, but really what does a gradient represent? It represents, if you remember from Math 1, the direction of maximal increase. It is the direction for which the function increases the maximum. Okay. Now we say, so if f is equal to a gradient to some function, we say that f is a gradient field. It's a vector field, but not any vector field. It's a gradient. We call it a gradient field because it's a gradient of some function. For example, the gradient field corresponding to the function f of x, y, z equal x squared plus y squared plus e to the z. So what is the gradient field corresponding is 2x, 2y, e to the z. This is the gradient field that corresponds to my function. Now I want to know the effect. So let's say I have a motion of some particle, and I have a vector field that acts on this particle moving. I want to know the effect of this vector field over the motion of the particle, which we usually call in physics the work of a force. Okay? So this is my goal, which means, does this force really, I have something that's moving, so independently I have a particle that is moving. Now, let's suppose I have a force at each point. I want to know if how this force is contributing to the motion. Is it like, is it a dragging force? Is it not contributing at all? Is it contributing maximally? And this is what we're gonna talk about. But before that, I need to introduce a notation. Given a curve C parameterized by the vector, r of t, we denote by t of t the unit tangent vector to C at a point r of t in the direction of motion. So I have a curve C, and this is maybe r of t. Now, t of t is tangent to the curve C. So what's the difference between t of t and the velocity? Because I also know that the velocity is tangent. The main point here that it's a unit vector. So this means, imply that t of t equal v of t over absolute value of v of t. It has the same direction as the velocity. Maybe the velocity is not unit. I mean, remember, the modulus of the velocity is the speed. which might not be equal to 1. Okay. Okay. So let's now try to define what's the work of a force. Okay, so work of a force. Now let's say I have a motion like this. Okay. And I have a vertical force at each point. And this is going from A to B. So what will be the work of F, which means how much is F contributing to the motion? You should know that the work of F is equal to 0. Because the perpendicular is a perpendicular since F is orthogonal to the motion. Do you agree? Now how can I make this the work? So in which direction the work of the force is maximal? So if I have moving from A to B like this, what will be the force that will contribute the most? What will be the direction of a force that will contribute the most to the motion? Is that if it is collinear. So in which direction? In the direction of the motion. The work of the force, the work of a force is maximal. Let's say the force is constant, and then the work of the force will be F. Oh well, maybe let's skip it till a bit later. But what if I'm moving, so third case, what if I'm moving this way? This is A, B, and this is my force. Okay? Then what will be the contribution of F? Now only the tangential component of F, in this case, contribute to the motion. By the way, it can contribute positively or negatively, but it's only for contribute. Which means here, in this case, if I take F to be this, F can be divided into two components. This is the tangential component, and this is the normal component. But this normal component is orthogonal to the motion, and this is the tangential component that is only contributing to the motion. So if this is alpha, what is the tangential component of the motion? The tangential component of the motion is F. So the tangential component is the absolute value of F times cosine alpha. Do you agree? This is now the work. Now this should be multiplied. Now this is the work at this point. Now the larger the distance, the larger the force. And let's go back here. Let's go back to this case. In this case, the work is what? The work is, in this case, this one, the work is absolute value of F times AB, correct? But in this case, the work is what? Is the absolute value of F cosine alpha, which is the tangential component of the work, times absolute value of AB. And this is nothing but F dot AB. But now if I want to write this in another way, I can write this as F dot AB over absolute value of AB times absolute value of AB. You all agree? Now, AB over absolute value of AB, in this case, since this is the line segment, this is the unit tangent vector. You agree? So this is really F dotted with t times absolute value of AB, where this is what we defined above. This is a unit tangent vector. And this is a way to calculate the work of a force, and in this case, when the force is constant. So it's F dot T times AB. Now let's generalize. So in general, let's stay with the weight. I have a motion, so a particle is moving. Well, not necessarily weight. Let's take in general the force. A particle is moving along a path C, and let F be a continuous vector field. So I have the motion, this is C, and I have a vector field, might be like this, might not be a constant vector field. So this is the F thing in yellow. Then what is the work of F? How do I calculate the work of F? This is C, this is moving from point A to point B. How do I calculate the work of F? Now, since F is not constant, I cannot use the whole thing, F dot AB, because, I mean, even the motion is not from A to B. The motion is not a straight line from A to B. The motion is just over the curve C. So what I should do is, as I did before, I divide this thing into, do it in another color. I divide this thing into a small line. So this is what I did. I divide the interval into small. Now these are approximately the line, line segment. Okay. So the work, let's say, the work of F is equal to what? Equal work, let's say, on pieces. So this is a work here. It's a work 1 plus work 2 plus work 3 plus work n. Where this is the work over delta S1. This is delta S1. This is the work over delta S2. This is the work over delta S3. This is delta S4. This is these pieces. This is the work over delta S2. So this is equal. Now I know that the work over delta S1 is F, as I used before, dotted with T. This is from here, times now the distance from this point to this point times delta S1. So this is approximately plus force dotted with T, but here the tangent is different, times delta S2 plus F dotted with T times delta Sn. So what I'm really doing is I'm dividing the line segment and dividing the curve into small pieces, and these small pieces are approximately line segments if I take them small enough. So this is equal summation from I equal 1 to n of F dotted T delta Si, which means, but is this exactly equal? No. But then how do I find the work if I apply it this way? Of course not. Then what I do, I take even more subintervals, then the work of F, I can write it as the limit as n goes to positive infinity of summation from I equal 1 to n F dotted with T delta Si, and this is equal integral over C, because you are evaluating over C, of F dotted with T ds. Correct? No, but this is a line integral. How do I calculate this line integral? This is called line integral, yes, of the vector field F over C. It's F dot the unit tangent times ds. But now in order to be able to calculate the line integral, I need to transform it into t. So this will be equal from integral from a to b. Now f dot t is as a function. Do you agree? Because this is scalar, it's a dot product. So I evaluate this function at r of t. Well, event function. Now what is t? This is t. This is t at r of t. Do you agree? And this is equal to what? V of t over absolute value of v of t. This is a unit tangent vector at each point r of t. Now what is ds? It's absolute value of v of t dt. And this is nothing but integral from a to b of f of r of t dotted, just that's, dot v of t dt. And this is how I compute integral over c of f dot t ds. Now another notation, so notation, since t is v of t over absolute value of v of t, and well, let's say this is equal. Now what is v of t? It is the derivative of the motion. What is the speed? It is the derivative of the arc length parameter. So sometimes we write, which is a good notation by the way, integral over c of f dot t ds to be what? To be integral over c of f dotted dr. This is just a notation, but these two things I calculate them this way. Now another notation, which is called the differential form notation. What is integral over c of f dotted with t ds is equal to integral over a to b of f dotted f of r of t dotted v of t dt, and this is equal integral from a to b of m and m of r of t, n of r of t, p of r of t. This is my vector field. Now what about v of t? V of t is x prime of t, y prime of t, z prime of t dt, and this is equal to integral from a to b of m of r of t, x prime of t, or dx dt, plus n of r of t, y prime of t, plus p of r of t, z prime of t dt. And this is equal, by notation, I know this integral over c. Now I go back to the line integral. Now x prime of t is dx dt, and here I have a dt, so this is called a differential form notation. This is equal integral over c of m dx plus n dy plus p dz. We're gonna use the three notation, so it's, and sometimes one notation will be easier than the other one, so it's very important to know the three of them. Okay, but the whole thing, I mean, when you want to calculate, this is my formula. And please, and now this is less up. I did this when I calculated the work of a force, but I don't have to have a force. It might be something else. So it might be just a vector field. So let's give the definition. So given a smooth curve C parameterized by the vector R of t, where a is smaller than t is smaller than b, and let f equal m and p be a continuous function in C, then the line integral of the vector field f over c is, so this is the definition. Now notation, integral over c, three notation very important. F dotted with t ds. It's very important to know what this is. This is f, t is a tangent to c in the direction of motion times ds, correct? And this is what we set the work. Yes, we proved this above. This is the tangential component of the vector field, and this is the distance. Another notation, this is equal integral over c of f dotted dr. Same thing. This is integral over c m dx plus n dy plus p dz. And when these are three line integrals, which all mean the same, this is integral from a to b of f, when I want to calculate it, f of rt dotted v of t dt, which is a dot product between the vector field and my velocity vector. Notice this is different than the line integral of a function. But now let's put some remark. First remark is that the line integral of a vector field across the integral of a vector field over C is the line integral of a vector field over C is independent of the parameterization. It's an exercise to prove. You can see the problem set. I gave you many hints on for this exercise for parameterization of C, which means, as you saw in the previous lecture, you can have many parameterization of the same curve, but for this definition to make sense, it should be independent of the parameterization. You should get the same answer whether you independently of how you parameterized it, as long as you parameterized it correctly. The second thing is if C equals C1 union C2, then integral of C of f dot t ds is equal to integral of C1 f dot t ds plus integral of C2 of f dotted with t ds. And this t is a tangent to the curve C. This t is a tangent to the curve C1, this t is a tangent to the curve C2. This if I have C1 that I know how to parameterize, for example, then C2. Third thing is, if minus C denotes the reverse path, then integral of minus C of f dotted t ds, in this case, is equal, let's say, the relation between these two. Now this is the tangent vector to the unit tangent vector to the motion with respect to minus C. This is the unit tangent vector to the motion with respect to C. So this unit, so if I'm moving this way, this is t. And if I'm moving the other way, this thing here, this is t. So I expect here to have a minus. And this you should know. Because the work of the force, if let's say the force is in the positive direction, when you reverse the path, the force will become in the negative direction. If I have a force, let's say, if I'm moving this way, and this is my force, and if I'm moving this way, and I still have this is my force, then here the force is negative of the force in this part. It should be. Now I just another, well, if F is a force, the line integral is called work. If F is the velocity field of a fluid, so I have a fluid that is having a velocity field, the line integral like a current. Let's say I have a current produced by a fluid. So this is then at each point the current is in some direction. In this case, F is a velocity field of a fluid. The line integral is called flow if F is the velocity, field of a fluid, and C is a loop, which means a closed curve. So the starting point, the ending point is the same, like for example this is my curve C. The line integral is called circulation. So mathematically, whether you are asked to calculate circulation, flow, or work, the three things mean the same, and they mean this. Okay. I'm gonna stop here, and in the next video, I will start doing example and finish section 15.2.